All right. Thank you. So sorry for the rough start here. But I want to thank everybody for coming today, and also for Weiji for organizing this symposium in Dave's honor, and for inviting me to present some of the work that I did in collaboration with Dave until very shortly before he passed away. So I have two disclaimers. One is that what I'm going to present is really a body of work that represents the thesis work of Laurel Isson, who is a graduate student co-advised by Dave and I between somewhere around 2008 and when she graduated in 2013. Unfortunately, Laurel couldn't be here in person, but she's certainly here in spirit and gave me a lot of help in putting this presentation together. So that's the first one. And the second one is just, like Paul was saying, this has got to be the hardest talk that I've ever had to put together, ever. And this is for two reasons. One being, obviously, the tragedy that gives this particular symposium its context. The second one being that Dave and I, not so much more Bonnell, but Dave and I really had very complementary expertise. I'm not a Bayesian modeler, and I'm not a computational neuroscientist by any stretch of the imagination. My background is in cell and molecular neuroscience, and I developed a very strong interest in the visual system when I came to Rochester as a postdoctoral fellow in 1995, so I actually arrived way before Dave did. And it was under the guidance of Tanya Pasternak, who's here, and Bill Merrigan, who were my postdoc advisors, that I developed an interest in actually measuring visual behavior, because I was really interested in broken visual systems, and especially how can we fix broken visual systems. And for that, I felt like I really needed to know how to measure behavior well. So how could two people as different as Dave and I, really come together to work together? And really that all comes down to being the Center for Visual Science. And that's one of the beauties of the center, that brings together people from completely different backgrounds and sometimes completely different interests. And so it was through hearing each other's students talk or each other talk that we kind of converged on a problem, which was a problem that was central to a particular patient population that I work with. And the problem is really summarized in the title here. So we work with patients who lose a large portion of their vision in adulthood. And work in my lab has tried to recover some of that vision lost. And we do recover some of the vision lost, and that's great. But a pervasive question that is always asked, for good reasons, of our work is, well, is the vision that you recover of any use to the patients, ultimately? So that is really where Dave came in and said, well, I think we can really design good experiments and measure this properly. So that's essentially how, and Laurel at the time was also very interested in doing some applied work and focusing the thesis on something that was applied. So it all was kind of a perfect storm, and we got together and started working together. So what is the problem that I'm dealing with in the patients in question? So these are patients who, let's see, I'll use my cursor here. So these are patients who have what we call either hemianopia or partial cortical blindness. It means that the input to their entire visual system, their eyes are perfectly fine, their lateral geniculars are even reasonably fine. Their damage is in primary visual cortex or the optic radiations or both. So that generates a blindness that is evoked through both eyes, and it affects the same part of the visual fields in both eyes. And the major causes of this are usually strokes, so this is extremely prevalent. Tumors can also cause this if they're in the right place, TBI, of course, trauma. The incidence is close to 1% of the general population over age 49. It's probably getting higher by the minute, especially given the number of young people we see in our research study nowadays. And I'm talking teenagers up, quite a few 30, 40-year-olds. So this is unfortunately something we'll probably see more of as we go. Among stroke victims, you look at percentages around 50% who may suffer from some of these visual problems. And the prognosis until fairly recently was that you couldn't do anything for these people. Unlike people with motor strokes, they don't get referred for any rehabilitation to speak of because there isn't anything validated out there yet. Hopefully that will change. So the deficit can improve a little bit in the first few months after the stroke, let's say, since that's 95% or more of these patients. And then, pretty much after those first 2 or 3 months, the deficit is stable and considered permanent. And as I mentioned, the dogma is that nothing can be done for them. And still to this day, most of these patients are sent home and told to get used to life, a very different life. And it's a very different life because obviously losing a large area of your visual field is going to cause problems in almost everything you do. I have a small slide here for just trying to explain why you get a blindness when you get a stroke in the brain. When your eyes are perfectly fine and they're providing input to the entire system. And so if you take a brain and you color the visual areas, this is functional MRI data, color the pulse color the visual areas. The yellow ones are the primary visual cortex, that's V1. That's the area that's damaged in these stroke patients. You can see that there are other colored areas there. There's other visual areas in there. So it's a little bit puzzling as to why you get a blindness when you just damage V1. And the reason is, if you look at this diagram, which is a flattened map of those cortical areas, if you want, you get most of the input from the eyes goes to the lateral geniculate nucleus. That goes directly here to V1, which is split into two. And then from V1, that information is distributed to the other visual areas. And of course, then when you lose V1, you tend to deprive all of these other visual areas of most of their input. So that's why you have a blindness. But the blindness is not absolute. Right? There's still, the LGN actually does send very small projections to all of these other areas, but they're very small. And under normal circumstances, we're not sure exactly what they do, but these tiny projections are probably what gives rise to the phenomenon of blind sight, which is this paradoxical phenomenon, whose term was coined by Weisskranz in the 70s, that essentially describes a process, a largely unconscious ability to actually process visual information presented in the blind field. And this is what gave us hope that we might be able to do something with these blind fields in the very beginning. So you might say, well, okay, these people have blind sight, so what's the big deal? Why are they so impaired? And in fact, one has to remember that blind sight is not seeing. And in fact, when you have blind sight that affects just one hemifield of the visual field, so if the lesion is unilateral, which is most of the time that's what it is, then having blind sight just affecting one blind field is not going to help you very much. And these people report verbally major impact on, as I mentioned, almost every aspect of daily life. But in particular, they complain of difficulties reading, inability to try, even though they do try, bumping into objects, difficulty navigating, walking around, familiar places, unfamiliar places especially. Going shopping is a real trauma. Going to a supermarket is a real traumatic experience for our people. And so this was a problem that that got Dave interested, and so therefore this is the context of all of this. So if we recover some of the vision in the blind field, is this going to be useful for these people? Is it going to help them deal with these problems? And to start answering that question, we had to ask, well, why do they have these problems, especially when they're unilateral lesions? So here's an example of some of the patients that we've worked with over the years. There's variety in the exact lesion location and the exact extent of the blind field. Some, like this, have a pretty clean hemifield defect, so they've lost vision over an entire hemifield all the way down the midline. All of them tend to have sparing of foveal vision, so they can fixate rather well, and they can look at things directly in front of them. Some of them have more sparing. in some parts of their blind field. So there's a bit of variability, right? All of them report problems navigating. So why? They have a completely intact half field. Why isn't that enough? Okay, so Dave thought that we should answer this question in the context of optic flow. That seemed to be a logical suggestion. So optic flow. Humans are very good for constant optic flow patterns. Humans are very good at discriminating very precisely the direction of heading from an optic flow pattern where you've got, especially where they can look directly around or at the focus of expansion. So the information around the focus of expansion right here is high quality and heavily utilized. And humans are very good at discriminating the location of that focus of expansion if they have access to this information. They're less good when they have to rely on information further away. And they are less good in different ways, which correlates with the quality of that information. Okay. So, okay, optic flow. Now there is some controversy that I'm aware of about the role of optic flow, or how much it is used to guide walking especially. So some people think that it contributes to walking, some people think that it may not, and some people say it depends on the fidelity of the information. So back to our patients then. We wanted to test a hypothesis that maybe one explanation for why hemianopes feel disoriented and have problems navigating in space is that they may have problems processing optic flow information. Now, you might think, well, even just logically speaking, that intuitively you can imagine that you'd have a hemianope who loses part of the vision and part of their visual field there on the right-hand side. As long as the focus of expansion and direction of heading information is present in their visible hemifield, in their intact hemifield, they have access to the most high-quality information there. Therefore, they should be pretty okay at discriminating direction of heading from that information. But if the blind field covers up that focus of expansion, how good are they? They are forced to rely on information that we know is less useful and should make them less accurate. So that's even without them doing anything weird to processing of that information. Okay, so that is the question we ask. How impaired are hemianopes at estimating direction of heading, which I'll refer to as DOH from here on, from optic flow? But before we could really attack the problem in hemianopic patients, we first had to test and figure out how normal observers performed on the exact experimental paradigm that we had to use subsequently in the hemianopes. And so, in particular, we wanted to know how well do normal observers estimate direction of heading from optic flow when the focus of expansion is obscured. So that all of our experiments have to have that condition in them. And then we wanted to, because hemianopes lose a hemifield of vision usually at a time, so we wanted to gauge how important are the 4 quadrants of the visual field in direction of heading estimates, and how important are the 2 hemifield, let's say left and right, in direction of heading estimates under normal circumstances. So the experimental paradigm that we used, these are experiments done in a virtual reality lab in the Center for Visual Science, and this is actually Laurel sitting in the setup. We did this using, we recruited 6 young adult subjects that were your typical undergraduates from campus. We projected a flow pattern, a large flow pattern, on this floor-to-ceiling cylindrical screen, 180-degree cylindrical screen, using a Krystel matrix projector. The experimenters were, the test subjects were viewing the pattern monocularly through the left eye in all cases. We used an eye tracker to monitor fixation precisely. And as you can see with Laurel here, she's holding a pointer. So this is a direction of heading estimation task. We present flow field. The person then responds by pointing where they think the direction of heading is on the screen. And then they click a mouse button to indicate that that's their response. The pointer had actually some markers on it that were tracked by an OptiTrack. So this is basically the basics of the experiment. Oh, the flow field as you can see in this schematic diagram, the central 10 degrees of the flow field was obscured because all of the directions of heading fell within that flow field. They were always at 3, 6, or 9 degrees eccentricity along these oblique axes. These are these little white dots. These are our focus of expansions or direction of heading. Fixation is at the center. And so the dots were actually, that were present on the screen, visible, were in an annulus that subtended from 10 to 20 degrees eccentricity all around. So that was the large field. We ran 3 different types of trials. I should go back to this for a minute. One set of trials were what we call wildcard trials, in which we actually had directions of heading that people were getting feedback on their responses for. That was about 25% of the trials. The rest of the trials were divided between anchor trials and perturbation trials. So anchor trials, you had the direction of heading, all of the dots on the screen moved in a way that was corresponding to one single direction of heading, 6 degrees, 3 degrees, 9 degrees, whatever it was on a particular trial. In order to estimate how much influence a particular quadrant had on this estimate, well, we played a trick. We created perturbation trials in which one quadrant's dots moved in a direction that was corresponded to a particular direction of heading, which is either 3 degrees or 9 degrees, while the other 3 quadrants had dots moving for a direction of heading at 6 degrees, let's say, eccentricity. So 3 quadrants told the same story, 1 quadrant told a different story. And that's how we estimated the influence of each quadrant in turn on a particular direction of heading. Okay. Is that reasonably clear? Yeah. Okay. All right. So, and of course, because we, and this was a collaboration with Dave, we had to run an ideal observer analysis too. So we wanted to see, of course, so the estimates that the young adults gave were then, we did a regression analysis to evaluate the components in the horizontal and vertical direction of their estimates. But then we ran a 10,000 simulation on an ideal observer, and the ideal observer was designed to basically to simulate performance which was only corrupted by sensory noise in the local motion estimates. So then we compared, but we essentially the stimuli generated we ran the ideal observer with were the same sort of stimuli that we ran the observers on. So then we compared the two, and this is what we found. Intact humans, young humans, are almost ideal observers. So this plot essentially plots the weight given to the vertical direction, the y direction, and the weight on the x direction, the horizontal estimate. Depending on which quadrant of the visual field the direction of heading is, or that we were particularly manipulating. So we find that humans, the ideal observers are always the dotted lines. The humans have the solid lines with standard errors represented by these ellipses at the tip. So ideal observer and the humans give most weight to the quadrant containing the direction of heading. Not exactly a huge surprise. The next 2 quadrants that they give the most weight to are the 2 flanking quadrants, the same hemifield, cross hemifield, the red and the green. And they give least weight to the quadrant that's diagonal to the one that carries the direction of heading. And that's in the orange over here. So humans really are almost like ideal observers. There are small differences, and this is actually data that, unfortunately, we submitted this paper literally days before Dave passed away. And the paper is about to come out. I saw the proofs literally 2 days ago. So it should come out in JOV very shortly. Okay, so back to the hemianopes then. So Dave's and Laurel's contribution to this really was to very precisely characterize and model their behavior. Because only then, this is Dave after all, so this is completely consistent with his philosophy. Only then can we ask the more interesting questions of, for instance, can you simulate the effects, the behavior of the hemianopes with a mask? Can you put an artificial scotoma on the visual field and get the same performance? Or are the hemianopes adapting to the deficit in weird and wonderful ways? That's one question. Are the heading estimates in the intact hemifield of hemianopes normal? We also know that hemianopes have blind sight. They can sense motion in their blind field. Do they use that information when performing a DOH test? So these are some of the questions we asked. Now, because these are hemianopes, and we've now had, instead of comparing the weight of different quadrants on how we estimate direction of heading, we had to modify the task in order to compare the impact of the left versus the right hemifield of the visual field, the half of the visual field. And to do this, we had, this photo was taken in front of that exact stimulus that you see in the background here with the long masks, not only just on the central 10 degrees, but also on the horizontal and vertical meridians. And here, we no longer worried about vertical estimates. We didn't really care about that. We just asked people to estimate direction heading along the horizontal axis, either to the left or to the right of the midline of the fixation spot. But otherwise, everything else was essentially the same. We recruited 3 groups of subjects for this. We recruited another batch of young adults, but then we recruited a certain number of hemianopes, so 7 of them, and they're older generally speaking, so we needed to also recruit a group of visually intact older adults that were age matched to the hemianopes. We ran everybody on 800 trials. It was a very painful experiment for all involved. And again, there were perturbation trials, but those perturbations were perturbations of an entire hemifield now, not just a quadrant. But otherwise, they were similar in principle. And we ran this in the full field condition or masked with a simulated hemianopia. So let's see, how do young adults do? We'll start with them on this field. So what I'm presenting here are nice little, they're actually very handy little summary diagrams. What you see in the circles represent the real target positions, the real direction of heading positions at 3, 6, 9 degrees of eccentricity on the left and the right hemifield. The triangles represent the perceived target, the average perceived target position, and you've got a standard error around each of those. Okay, so this is how young adults do it. If you look at the nitty-gritty of it, they're pretty good. They can tell left from right, most of them, which is nice. Interestingly, you know, the spots that are really closer to fixation, they tend to estimate them closer to fixation than they really are. The middle spot, they're pretty spot on. The furthest spot, they estimated beyond what it really is, more eccentric. Okay? So how do older adults do? Those are visually intact, completely different story. And in this case, I think you can see fairly clearly that they seem to be compressing where they're estimating. They estimate everything to be closer to the fixation than it really is. One may speculate as to why, but I won't go into that. Okay, so we did, again, a regression analysis on these estimates, and here the purpose was to extract a number of potentially interesting factors, like, for instance, compression or expansion factor, which you can see as you can consider this a multiplicative bias, if you want, which has smaller effect closer to fixation, greater effect further out. The weight given to the left versus the right hemifield is part of this equation here about the first term. And then there's the beta, which is an additive response bias. So that moves the estimate linearly to the right or the left. Okay, and then there's noise, of course. All right. So what do we have? So these are the young adults, again, you know, older adults, and if you actually plot the compression expansion factor, the multiplicative bias, you see that for both of them, the red is the left hemifield, right hemifield, blue is the left hemifield. There's no significant differences between the hemifields in most of these factors estimate. And the young adults, though, they anything bigger than 1 on this factor means that they're expanding, which actually, you know, they generally apparently expand on their estimates of where things really, of the direction of heading is, whereas the older adults don't. They're closer to 1, which means they don't have much of that factor. Both of them, however, have this negative additive bias, which means that they're squishing everything linearly towards fixation. And that, in the younger adults, it compensates close to fixation. It compensates a little bit for their expansion, but not so much in the higher eccentricities. And unsurprisingly, everybody gives in the gray here, more weight to the quadrant, or the hemifield containing the direction of heading. Okay. Than they do to the other hemifield. Now, if you take the older adults and simulate a hemianopia, so you put a mask over half of one of the hemifields, they do things a little bit differently. So I'll point your eyes towards the average plots down the bottom here. And let's start with a good field. In the good field, they're perfect. In the visible part of the field, they are now perfect. These are older adults. They were massively compressed towards the center previously. Not anymore in the intact hemifield. But they still are compressed on the blind field. The surprising result, though, is that they can still tell, even though they can't see where the direction, the focus of expansion is, they can still tell whether it was generally in the left or generally to the right. That they're still got right. But their precise estimates are have a different behavior than if you don't put a stimulated hemianopia on half of the field. Okay, and you can compute them, you can plot this. So the compression expansion factor, this multiplicative bias, if you take the visible hemifield, they're still compressing. They're less so than if they don't have the hemianopia, but their additive bias goes positive instead of being negative. So that's why they're expanding away from fixation now. All right. So that's why they compensate for this greater compression by having some additive bias. In the blind field, however, they compress even more, but they're no longer compensating. And that's why you've got this error, much larger error in the blind field. Okay, moving on. Okay, what about the real hemianopes now? Well, so this is what they look like. And they are really quite different, even from the older adults with the simulated hemianopia. And this is the average plot. So let's take it one step at a time. In the intact hemifield, I'm going to put the graphs up here for the compression expansion factor and the additive bias on the bottom. The black marks are the simulated hemianopia data, and the green ones, the greenish ones, are the ones from the real hemianopes. So on average, if you take a look at the intact hemifield division, the hemianopes make huge mistakes. It's like they're expanding, they have an expansion factor going on here. They're estimating everything being further away from the fixation point. Interestingly, in the blind field, they make huge errors also. And it's almost like the errors are also drawn towards the intact hemifield. And so in the visible hemifield, and in the blind field, there's huge compression factors. They're compressing the information closer to their fixation. But in the intact hemifield, they have a huge positive bias, additive bias, which means that they're really, everything is biased towards the hemifield. And similarly in the blind field, one of the others is in the blind field. So the real hemianopes, or real hemianopia, is a completely different picture yet again. It's not like simulated hemianopia. Okay, and the hemianopes give significant weight to information in the blind field. That's the other thing. Less so than the intact, visually intact older adults, but still significant. And there are some that are higher than the other two. Well, the two that are higher are these two subjects. The two that are lower are these two subjects. So for these two on the right, we actually had to use a quadrant mask to mask the sparing in their upper field, upper quadrant. So we halved the amount of information available to their blind field, and that may be why their values are about half of that of the other two. So we need a lot more data to really nail this particular phenomenon down, but it's nevertheless important to see that they do give weight, unprompted, automatically, to motion information in their blind field. So that matters. So I'm just summarizing here. So bottom line is that hemianopes are impaired at estimating direction of heading from optic flow. This impairment is not fully captured by simulating hemianopia. So they are, so simulated hemianopia underestimates the real behavior. Surprisingly, in many ways to us, the deficit also affects the intact field of vision in the hemianopes, not just the blind field. And as far as the blind field is concerned, these people give significant weight to the information contained in it. What are the implications? There are many. The fact that real hemianopia is more exaggerated than a simulated deficit could represent an adaptation to this deficit in processing, I would think. The fact that the DOH judgments are actually impaired across the whole hemifield may explain why these people have persistent problems navigating, even if their intact hemifield is not providing accurate information about direction of heading. And finally, the fact that they give weight to the blind field, while it may contribute to the disability itself, because it's not accurate information, but there's a silver lining, because we are trying to improve and we train in motion discrimination, especially global motion discrimination, in the blind field of these subjects. That is essentially our approach. This may actually be more important than we think, potentially, because if we can actually improve motion processing in this blind field and they rely on it automatically, it may actually improve their ability to estimate direction of heading as well. All right, and on that note, thank you for your attention, and I want to thank everybody who's collaborated to our work over the years, but of course, mostly David, for his insights and his friendship, and for taking this work in directions I would never have taken it on my own, for sure. Laurel for doing all of the hard work, and I should mention also Keith Parkins, who is a programmer extraordinaire, making all of the technology work together well. And thank you for your attention.